Flights in lighter-than aircraft have taken place since the late 18th century, and experiments with man-carrying gliders began in the 19th century. But the lack of a suitably lightweight and efficient power plant delayed the first successful powered flight until 1903, at the dawn of the 20th century. The steam engine, which was invented in the early 1700s, was heavy and inefficient. Because combustion took place outside of the engine, it was termed an external combustion engine. Over 90% of the heat energy produced in the steam engine was wasted. In 1876, Beau de Rochat developed an engine where the combustion process took place inside the engine, but it was Dr. Otto who first succeeded in producing a working engine based on the internal combustion principle. The principle of operation of the engine is accomplished by inducing a mixture of air and fuel into a cylinder, which is then compressed by a piston. The mixture is ignited, and the rapid rise in temperature causes the gas pressure in the cylinder to rise and forces the piston down the cylinder. Linear movement of the piston is converted into rotary motion by a connecting rod and crankshaft. The burnt gases are then exhausted to atmosphere. The engine thus converts heat energy into mechanical energy. The internal combustion engines fall into four main categories: compression ignition engines, or diesels, two-stroke and four-stroke spark ignition engines, Wankel rotary engines, and gas turbine turboprop engines. This lesson covers in detail the construction and operation of the four-stroke reciprocating engine, which is commonly used in aviation and generally referred to as the piston engine. Before we look at the operation and construction of the piston engine, however, an understanding of the following terms, definitions, and theories will be required. A force is that which, when acting on a body which is free to move, causes it to move, or conversely, that which stops or changes the direction of a moving body. The units of force are newtons or pounds force. Force is produced when a mass is accelerated. Force equals mass times acceleration. A force is used to move the piston down the cylinder in an engine. The work done by a force is defined as the product of the force and the distance moved in the direction of the applied force. For example, the piston is moved from the top to the bottom of the cylinder by a force. The units of work done are joules or foot-pounds. Thus, work is done when the piston is moved a distance from the top of a cylinder to the bottom of a cylinder by a force. Energy is the capacity of a body to do work, and it comes in many forms. For instance, heat energy, which we convert into mechanical energy in the steam engine. Light, which can be converted into electrical energy in a photoelectric cell. Chemical energy, which can also be converted into electrical energy in a battery. Kinetic energy, which a glider flying at high speed has, can be converted into potential energy if the glider suddenly climbs. Conversely, the potential energy thus gained can be converted into kinetic energy if the glider dives from its newfound altitude. The unit of energy is the joule. You'll notice that we use the term converted when referring to the process of changing one form of energy into another. This was deliberate because the law of conservation of energy states that energy can be neither created nor destroyed, only its form may be changed. For instance, the chemical energy of the fuel is converted to heat energy during combustion in the engine. The engine then converts this to mechanical energy. Power is the rate of doing work. It can be expressed as work done per unit time. Work is done as the piston moves in the cylinder. It's moved by a force a certain distance a number of times a minute, and so the power thus generated can be measured. The unit of power is either joules per second, which equals watts, or foot-pounds per minute, equating to horsepower. The horsepower is a measurement of power which is equal to 33,000 foot-pounds a minute. Dynamics is the study of energy. Newton's laws of motion deal with the properties of moving objects. It's easy in this illustration to see the pistons or the crankshaft move. But air also has mass, and will obey Newton's laws. We must remember that air is the working fluid within the engine, and the fact that it has mass, which means it also has inertia, will become very significant to us soon. Newton's first law of motion states that which is still will tend to remain still, and that which is moving will tend to continue moving, and will resist any change of speed or direction. In this animation, it can be seen that the white ball is initially still, until it's struck by the cue, when it starts to move. It continues in a straight line until it strikes the red ball, when it's deflected off at an angle. The first law of motion can be made relevant to the piston engine, if we remember that the mixture of air and fuel vapour in the induction system of an engine must have a force applied to it to get it moving into the cylinder. Once the mixture gets moving, its inertia will keep it moving until the increasing pressure in the cylinder opposes that movement. Newton's second law of motion states that if it is required to alter the state of rest or uniform motion of a body, or change its direction, a force must be applied to it, and the more sudden the change desired, and the greater the mass affected, the greater the force required. The second golf ball has to be moved further than the first. In the first case, the club used is a 7-iron. In the second case, it's a driver. The golfer in both cases uses exactly the same swing. The relevance of Newton's second law to the piston engine can be illustrated by imagining the force required to move the piston in the cylinder. If the engine is only lightly loaded, as shown here with the aircraft in a shallow dive, then just a small force on the piston will be required to move it. If, on the other hand, the engine is under load, as it is here during a take-off and climb, then a greater force will be required to push the piston down in the cylinder. We've indicated this by increasing the number and size of the arrows pushing the pistons down. Newton's third law states that the application of a force upon a body will cause an equal and opposite reaction upon the surface which produces the force. A practical demonstration of the effect of Newton's third law is probably best found in the gas turbine engine or the rocket. The acceleration of gases from the rear of either of these machines generates a reactive force which propels them forward. Thermodynamics is the field of physics that studies the properties of systems that have a temperature and involve the flow of energy from one place to another. The first law of thermodynamics states that heat and mechanical energy are mutually convertible, and the rate of exchange is constant and can be measured. To bring this law into the context of piston engines, imagine two metal surfaces being rubbed together without lubrication. Heat will be generated, and this can be measured with a temperature gauge. This is an example of mechanical energy converted into heat energy. Conversely, when fuel is burnt in a piston engine, the heat energy in the fuel is converted to mechanical energy by the action of the pistons and the crankshaft. This mechanical energy can also be measured. In this case, we show a dynamometer measuring the power output of an automobile engine. The second law of thermodynamics states that heat cannot be transferred from a region at a lower temperature to one at a higher temperature without the expenditure of energy from an external source. As an example of this phenomenon, you will have noticed that whilst heat will naturally flow from a radiator to the colder atmosphere which surrounds it, the expenditure of energy is required to lower the temperature of a refrigerator to a level below that of the surrounding atmosphere.